Okay, I'm going to be working on the homework for 8.5, which is power series. I'm starting with number 3. Number 3 is the power series sum n equals 1 to infinity of -1 to the n times n times x to the n. And the instructions here are telling us to find the radius of convergence and the interval of convergence. So to do this, we're going to use the ratio test. So ratio test, remember what we want. I do that all the time. What we want is for the ratio test to give us something less than 1. If we get something less than 1, then we know it converges. So I'm going to take the limit as n goes to infinity of, let's see if I can find a decent marker here. This with n plus 1 plugged in. Over this without, with just n plugged in. And since these were not fractions, I'm just going to leave it like this, so I don't have to flip anything over. And I need this to be less than 1, right? This is what we want. We want this to be less than 1 in order to have convergence. I don't have to pay attention to the negative ones. I can rewrite my x to the n plus 1 as, I'll do that right now, x to the n times x. And that allows me to cancel out these x to the n's. So what I have now is the limit as n goes to infinity. The absolute value, I have an n plus 1 on top over n on the bottom. And notice I'm separating all of that from the x term, or the x factor, which is here. I want that to be less than 1. Now, n is only impacting this piece right here. It has no impact on x. So if I let n go to infinity, I get infinity over infinity here. So a quick application of L'Hopital's rule tells me that this is going to be a 1. So 1 times x, absolute value. I need that to be less than 1. So I just need the absolute value of x to be less than 1. So remember, to find your radius of convergence, you're looking for something like x minus a less than capital R. And in this particular problem, a is 0, right? If a is 0 here, we have this. So that means right now for me, my radius of convergence is 1. Now, to find the interval of convergence, what I need to look at is what would happen if I had actually let this limit, what if it were equal to 1? So remember, if this is equal to 1 here, the ratio test is inconclusive. So I ask myself, well, what would happen if that was 1? What happens if this is 1? So this is where we get our interval of convergence from. So we know right now, we know that the series converges right now if the absolute value of x is less than 1, which means that x is between -1 and +1. So that's what we know so far. The question, what we want to still know, is what happens at the end points? In other words, if x is equal to 1 or x is equal to -1. So what happens if I actually go to these endpoints? We know the ratio test will fail us. So what we'll do is we'll look at each situation separately. So first let's start off, let's let x be equal to 1. So we're just going to look at this one right now. If x is 1, let me rewrite the series. I'm going to replace this with 1. So I get sum n equals 1 to infinity of negative 1 to the n times n times 1 to the n. But 1 to the n, right, 1 to any power should just be 1. So this is just a 1, so it really isn't even there. And I get this. So what does this sum do? So now we're back in the previous sections. There's no more x involved here. I just want to know if this is a convergent or divergent series. Well, I can just do a quick nth term test on this and realize that if I just look at the limit as n goes to infinity of just this piece right here, that goes to infinity. And of course, if it's switching signs, this thing is not going to 0 no matter what. And the nth term test tells us that if that happens, it diverges. So that tells me if I let x be equal to 1, I'm going to get a divergent. It diverges. So I'm going to get a divergent series if x is 1. So that means that I'm trying to find the interval of convergence. So I want to know where it converges. Right now, I know that x has to be strictly less than 1, greater than negative. I already knew that coming in. I was checking to see right now if I could include 1 or not. And it turns out that I cannot include 1 or else it will diverge. So I don't want that. That's what I know so far. But now I need to check this one. So now what I'll do is I'll rewrite the series again. Let x be negative 1. The series becomes sum n equals 1 to infinity, negative 1 to the n times negative 1 to the n. And these two can actually come together, right? Negative 1 to the n times negative 1 to the n is negative 1 times negative 1 to the n, which is just 1 to the n, which is just 1. So this series becomes n equals 1 to infinity of just n. And of course, if I do the nth term on this, again, take the n, that's going to go to infinity, right? If I take the limit, and that's definitely not 0. So again, it will diverge. So I am not going to include negative 1. I do not want that to happen, or it will diverge. So in summary, final answer here for this series. The radius of convergence is 1. The interval of convergence is the interval negative 1, positive 1, not including the endpoints. So if I did want the endpoints, I would have done this. Okay, but I don't want the endpoints, so that's it. All right, let's take a look at number 2. Sum n equals 1 to infinity. Let's see, I'm recording, right? Negative 1 to the n, x to the n over the cube root of n. All right, so let's try the ratio test to figure out if we can get a radius and convergence. I want to take the limit as n goes to infinity of, okay, so since I have a fraction here, I'm going to be flipping and stuff. I do negative 1 to the n plus 1 times x to the n plus 1, which is x to the n times x. We've done that a lot. And then down here, cube root of n plus 1. That over this, so it flips, and we get cube root of n here. On the bottom, we get negative 1 to the n, x to the n. Now, we need that to be less than 1 in order to have convergence, right? So we want this to be true. And we start getting some cancellation here. X to the n, x to the n. These don't matter because I'm doing absolute value. And so now I'm at this point. I have the limit as n goes to infinity. Absolute value, let's see. I'm going to separate the n stuff from the x stuff. cube root of n over cube root of n plus 1 times, again, just an x, less than 1 is what I need. And so we got to figure out what happens now as n goes to infinity. So what I would do here to figure out what's happening, because this gets infinite and that gets infinite, we could use L'Hopital. I don't want to take derivative of a cube root, so what I'm going to do is instead of writing that, I'm going to just turn this into one root. So it's just going to be like this, cube root of n over n plus 1 times x, which is just properties of radicals. And now I'm going to take the limit, I'm going to pass it through the radical, I'm going to take the limit in here. That's going to be infinity over infinity. Do L'Hopital one time, we're going to get 1. Cube root of 1 is 1. So this, again, is just turning out to be absolute value of x less than 1. And that looks like the right form, right? This looks like this. So in this case, the radius of convergence is, again, 1. I had a feeling that was going to happen. Give me just a second. There it is. OK. So we have a radius of convergence of 1 again. Now, again, I have to figure out what's the interval of convergence. And so I have to test the endpoints. So I know that this absolute value really means that x is greater than -1 and less than +1. So I've got to check the two endpoints to see whether or not I converge or diverge there. So let's check each one individually. I'll start with letting x be 1 first. And I rewrite the sum, n equals 1 to infinity, and wherever I saw x, I replace it with 1, positive 1. So I get -1 to the n, and then x was 1, so 1 to the n over cube root of n. And of course, 1 to the n is just 1, so I don't even need it there. And so I want to figure out if this series converges or diverges. Well, that's an alternating series. And so I think I'm going to use the alternating series test. So I'm going to identify b sub n first, which is this piece right here. So b sub n is 1 over the cube root of n. I have to check two things. Remember, I have to show it's decreasing, and then the other thing I have to show is that the limit of that goes to 0. So I'm going to do that part first, because it looks like the easier part. That limit is 0, so that checks. Now all I need is to show that b sub n is greater than b sub n plus 1, so that it's a decreasing sequence. So let's do that. I'm going to do b sub n here. I need to show that 1 over cube root of n is greater than 1 over cube root of n plus 1. And I could just stop right there and say yes, because the numerators are exactly the same. This denominator is smaller than this one. Or you could say this one is bigger than this one, which means this fraction is smaller. But you could also just do your little kind of algebraic simplification here. That's obvious, but I'll cube both sides. And I'll subtract n on both sides. I get 1's greater than 0. That checks. So this is, therefore, this converges, which means that when I do this, I get convergence. So I do want to let x be 1. That's OK. If x is 1, I'm still going to have a convergent series. Now, let's look what happens if I let x be -1. So if I let x be the other endpoint, so keep in mind, what I'm doing is I had this, and I was checking the endpoints. I checked 1 and it worked, so I am going to include it. Now I just need to figure out if I need to include -1. So sum n equals 1 to infinity, -1 to the n times, it was x to the n, so -1 to the n again over cube root of n. Just double check that, yes. And this is just sum n equals 1 to infinity. And we just did this in the previous problem. When you put those two together, that's just a 1. And then cube root of n. And now we no longer have an alternating series. But that series, hopefully you recognize, 1 over n to the 1/3 power. That is a p series. P is a third, which is less than 1, which means we get divergence. And that means if I let x be -1, I get divergence, which I don't want. So that means my interval of convergence is actually this right here. So my interval of convergence is the interval -1 to +1, including +1, but not including -1. And of course, my radius of convergence was equal to 1. We knew that to start. So that is number, which number is that? I say this number 4, right? Did I say 2? It's number 4. So, all right, let's go on to 5. Still getting over this thing I've got. I have no idea. It's crazy. I feel better than I did the other day, though. All right, so number 5. Sum n equals 1 to infinity, x to the n over 2n minus 1. All right, ratio test. I'm going to do limit, n goes to infinity, absolute value. Plug in n plus 1 first, so x to the n times x. Bottom, plug in n plus 1 right there. Be real careful there. It's 2n. Distribute through, we should get plus 1. So replace that with n plus 1, distribute the 2 through, subtract 1, you should get that. And then I'm going to divide this by that, so I flip it. 2n minus 1 over, x to the n. I need that to be less than 1. So let's see what happens here. Cancellation. And now I'm going to rewrite this limit. I'm going to split my n's away from my x's. So I have a limit, n goes to infinity, absolute value of 2n minus 1 over 2n plus 1 times, I just had an x there again. Need that to be less than 1. And then right here, infinity over infinity again, L'Hopital, we're actually going to get 1. Okay, so right, you do derivative on top, you get 2, bottom 2, divide, you just get 1. So absolute value of x less than 1. Same story, radius of convergence is 1 here. And now I need to check the endpoints. So I know this is true. I'm going to converge here, but check the endpoints now. So far, every problem we've done, we've had a radius of convergence of 1, and we've had pretty much the same interval every time. They're going to get more interesting, I promise. So now, check endpoints. So I'll check, doesn't matter which one you start with. I'm going to let x be 1. If x is 1, this sum becomes n equals 1 to infinity. It was x to the n over 2n minus 1, I believe. Yes, and of course 1 to any power is just 1. And do you recognize this? Harmonic diverges. So this diverges, which means we do not want to include 1, right? We do not want 1, so I'm going to put the red here. That's what we have for sure. We don't want to include 1. Now let's let x be -1. If x is -1, it becomes -1 to the n over 2n minus 1. This is no longer harmonic. This is an alternating harmonic, and I need to use alternating series test for this. So when I do alternating series test, I identify b sub n, which is the positive part of this, which is that. I'll check the second condition. The limit as n goes to infinity of this is obviously 0, so that's nice. And now I need to show it's decreasing. So I want to show that b sub n is greater than b sub n plus 1. I'll do it up here. B sub n is 1 over 2n minus 1. I want to show that that's greater than 1 over 2n plus 1. So that's what happens if you plug n plus 1 in there and distribute. We did it earlier, so that. And then go ahead and clean this up. 2n plus 1 greater than 2n minus 1. Subtract 2n from both sides. 1 greater than negative 1. Check. So what does that mean? Therefore, it converges. So if I let x be negative 1, this converges, which is what we want. So that means, I erased it, negative 1 less than x less than 1. I do want it to be negative 1. So my interval is going to be the closed and negative 1, and then the open end over here. My radius of convergence was 1. All right, that was number 5. Number 6. Sum n equals 1 to infinity, negative 1 to the n, x to the n over n squared. Okay, start with my ratio test. Limit n goes to infinity of, let's see, plug in n plus 1 up here. N plus 1 squared down on the bottom. Divide this by that, flip it. N squared on top, on the bottom. Negative 1 to the n, x to the n. Cancellation here. These don't matter. And now I'll split off my n squared stuff from my from my x's. So limit n goes to infinity. Let's see. N squared over n plus 1 squared times, again, I've got x there. I need that less than 1. Oops, I forgot less than 1. Now, this is infinity over infinity, but I'm going to expand the bottom out. N plus 1 squared is n squared plus 2n plus 1. And I'm kind of getting bored of this, having the same interval every time, but it'll change, I promise. Let n go to infinity, infinity over infinity, L'Hopital twice, and you should get 1. So this is going to be absolute value of x is less than 1, which means my radius of convergence is 1. I know so far that this is true. It's going to converge as long as the absolute, as long as x is between these two numbers. This will converge, and so I just need to check the endpoints. So let me check 1. I rewrite the sum. N equals 1 to infinity. I've already forgotten what it is. Negative 1 to the n, and then 1 to the n over n squared. And of course, this is 1. And that's an alternating series. So I'm going to do alternating series test. B sub n is just 1 over n squared. It's pretty obvious that 1 over n squared converges to 0. So I'm not writing the limit anymore. That's obvious. And then the first thing it shows it's decreasing. So I want to show b sub n is greater than b sub n plus 1. I need to show 1 over n squared is greater than 1 over n plus 1 squared. And this is n plus 1 squared is greater than n squared. That's obvious, but I'll do it again. So 2n plus 1 is greater than 0. That checks off. So this converges. If x is 1, we converge. So that's good. I want to include it. And then now I'm going to let x be negative 1. Let x be negative 1. series becomes n equals 1 to infinity, negative 1 to the n, again negative 1 to the n over n squared. And that's just sum n equals 1 to infinity, 1 over n squared. This is a p series. P is 2, which is greater than 1. Therefore, it converges. And so it converges on both ends when x is 1 and negative 1. So I want to include them both. So my interval of convergence is the interval negative 1, 1, including both, so brackets on both. All right. So far, these have not really become too crazy. I have a feeling that's coming. But we're only on number 7 out of 22 problems or so. So number 7. Sum n equals 0 to infinity, x to the n over n factorial. So I'm going to do my ratio test. Limit n goes to infinity. The absolute value, plug n plus 1 in here. When I plug in n plus 1 factorial, we've already seen that that can be broken down to be this. And then I do this over that, flipped over, n factorial on top, x to the n on the bottom. I want this less than 1. N factorials cancel, x to the n's cancel. And so I get limit n goes to infinity. Okay, split the n's from the x's. So all I have is an n plus 1 on the bottom, so I'm going to write that as 1 over n plus 1. And then over here I have x. I need that to be less than 1. So if I let n go to infinity now, this goes to 0. And then it doesn't matter what x is. Because no matter what x is, if I fix an x and I let n go to infinity here, this left side is going to be 0. And that's always going to be less than 1. So regardless of x, this is going to converge, regardless of x. That means for any x, the series converges. So what does that mean in terms of the radius of convergence? Well, the radius of convergence is the interval, how big the interval is that x lies in. And since it can be any number, this would be an infinite interval. So it'd be everything. And then the way we say that as an interval is negative infinity to positive infinity. All right. Next. Eight. Sum n equals 1 to infinity. X to the n over n times 3 to the n. Set up my ratio test. Limit n goes to infinity of, see, plug n plus 1 in there, x to the n times x, over n plus 1 times 3 to the n plus 1 is 3 to the n times 3. And then multiply by the reciprocal of that, so n on top, 3 to the n here, x to the n on the bottom. I need that to be less than 1. Lots of good cancellation here. Gone, 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 gone. I'll put all my n stuff together and all my x stuff together. Limit, n goes to infinity. All right, let me put my x down here. And then I have an n on top. And on the bottom, I have n plus 1 and 3. I'll distribute the 3 through. 3n plus 3. It's multiplied. So what happens as n goes to infinity now? Well, as n goes to infinity, we infinity over infinity. So if we do L'Hopital one time, what we're going to get is 1/3 times x needs to be less than 1. So finally, we have something that's a little different. Remember, we need our radius of convergence to be like this, which means that we need the coefficient on x to be a 1, and the coefficient on x right now is 1/3. And then, of course, a here for us is 0, so we're not even really considering the a. So this is the same as 1/3 times the absolute value of x, because 1/3 is always a positive number. And now I multiply both sides by 3. Absolute value of x is less than 3. So my radius of convergence for this problem is 3. It's this number on this side. Now, what does this mean? It means that my interval of convergence so far, I know x must be less than 3 and greater than -3. The question is what happens at the endpoints. So now, instead of letting x be 1 and -1 the way we've done the entire homework assignment so far, I'm actually going to let x be 3 and -3. So let's start with 3. Let's rewrite the sum. N equals 1 to infinity. It was x to the n on top. There's x to the n. And then I had n times 3 to the n, right? Yep. And it was n equals 1. Okay. So, oh, wow, look at this. These cancel. Sum n equals 1 to infinity of 1 over n. Harmonic. Diverges. So that means I do not want to include +3, or else it'll diverge. So it's going to be a strict inequality just like that. Now I'm going to let x be -3. Let's see how that changes things, or if it even does. -3 to the n over n times 3 to the n. Now I can't cancel those. Not yet. Do this. So on the top I'm going to write -1 to the n times 3 to the n over n times 3 to the n. So I peeled the negative off the 3 like that, which I'm allowed to do as long as I raise it to the n power. Those two would go back together to become this. And now 3 to the n over 3 to the n cancel. And you're left with sum n equals 1 to infinity of -1 to the n over n. And this is an alternating series. You could use the alternating series test to check this. I'm not going to do it. B sub n would be 1 over n. And this is an alternating harmonic series. This converges if you run the test. So that means if x is -3, I do get convergence, which means I do want to include it, which means my interval of convergence should be the interval including -3, so bracket -3 to 3, but don't include 3. Take a quick little break here. Okay, number 9. Sum equals 1 to infinity, negative 1 to the n squared x to the n over 2 to the n. And it's starting to get a little more complicated now. All right, ratio test. Limit n goes to infinity. Okay, plug n plus 1 into this. Negative 1 to the n plus 1 times, right here, n plus 1 squared times n plus 1 here, x to the n times x over n plus 1 here, 2 to the n times 2. Division of this, or take this and divide by that, flip it. So on top you have 2 to the n. On the bottom you have all the other junk. So negative 1 to the n squared, x to the n. I need that to be less than 1. All right, let's see what kind of cancellation I get here. X to the n's, 2 to the n's. Negative 1s don't matter. And so I'll rewrite this. Limit n goes to infinity. Get all the n stuff together. So I have this right here. I'm gonna expand that. So that's n squared plus 2n plus 1 over, on the bottom I have a 2 and I have an n squared. So 2n squared times, in terms of x, I just have that x right there. Need that to be less than 1. And if I use L'Hopital's rule on this piece, I'm going to get 1/2. So this is going to turn out to say 1/2 absolute value, 1/2 times x needs to be less than 1. And very similar to the previous problem, I'm going to bring the 1/2 out of the absolute value, and then I'm going to multiply both sides by 2. So my radius of convergence is 2, and this means that x must be less than 2 and greater than negative 2. So I need to check 2 endpoints. I need to first let x be 2. And rewrite that with x2 in there, x being 2. Sum n equal 1 to infinity, a negative 1 to the n times n squared times, this is 2 to the n, and then over 2 to the n. This cancels out, and so I get sum n equals 1 to infinity of negative 1 to the n times n squared. This diverges by the nth term test. As n goes to infinity, that goes to infinity, and that's not going to 0, and it's flipping back and forth, so it's divergent, so I will not include 2. Now, if I try negative 2, then what changes here, negative 2 to the n over 2 to the n. So I have to do a little bit of work here. I'm just going to peel off a negative 1 to the n, 2 to the n, that's just this, over 2 to the n, and these cancel. And then when I put this and this together, I just get a 1. So I have sum n equals 1 to infinity of n squared. And of course, this diverges also by the nth term test. So that means I don't want to include either endpoint. I just want to have this interval. So interval is going to be equal to negative 2 to 2. And that was number 9. Okay. Number 10. Okay, I've got sum n equals 1 to infinity of n to the n times x to the n. I'm going to do a ratio test on this. Might be able to do a root test instead, but I'm going to do a ratio test. So plug in n plus 1, you get n plus 1 to the n plus 1 times x to the n times x. So that's what happens when I plug n plus 1 in there. Divide that by, since it's not a fraction to start, I don't have to do that flippy thing. N to the n plus times x to the n. Need that to be less than 1. These cancel. These don't cancel, but I can clean it up still a little bit. Limit n goes to infinity. This top one here is n plus 1 to the n times n plus 1. So that's splitting that into two pieces. And then over n to the n, and then times x, because I had that x there. I need that less than 1. And so if I let n go to infinity here, I've got infinity over infinity, but L'Hopital's rule is not as clean there. So let me rewrite that a little bit, make it a little easier to work with. All right, since these are both to the n power, I'm going to do n plus 1 over n to the n power times, I still had n plus 1 here, then I still had x out here. And now what I want to know is what happens as n goes to infinity. Well, if n goes to infinity, I know in here with L'Hopital I get a 1, so this is approaching 1, and this is approaching infinity, and we saw that before that's a problem. We have to figure that out. So I'm going to have to figure that out on the side here. So separate work. What is the limit as n goes to infinity of n plus 1 over n to the n? And this is where I come in, I call this y, and I take natural log on both sides. So natural log of y equals, when I do the natural log here, it passes into the limit, and the n comes down. So limit n goes to infinity of the n came down, natural log of n plus 1 over n. And I think what I'll do is I'll rewrite this, I'll rewrite that in there as 1 plus 1 over n. And I did that, to split it into two different fractions. All right, so what happens here? I need to now take that n that's out front, drop it to the denominator. When I drop that down, it becomes a 1 over n. And now I should be able to use L'Hopital on that. So when I do L'Hopital here, I do natural log y equals limit n goes to infinity. I'm using L'Hopital's rule here. Derivative of the top is 1 over 1 plus 1 over n. So that's derivative natural log of something. Then derivative of what's inside. So times derivative 1 is 0. Derivative of 1 over n is negative 1 over n squared. Over the derivative of the bottom, which again is negative 1 over n squared. These cancel. Now let n go to infinity. This goes to 0. You get 1 over 1. So you get that natural log of y equals 1. And then you take e on both sides. E to the natural log of y equals e to the 1. So y is e. So coming back here, I know that what happens is that this piece just alone goes to e, which is a number, but then times this piece, which goes to infinity, times x. I need that to be less than 1. Well, that's not going to happen. Okay, so as n goes to infinity, this gets huge. The only way that I'm ever going to get this under control and make this smaller than 1 is if I were to let x be 0. If x was 0 to start the whole problem, then this would be true. So, since that's the only way I can get control over this and make it converge, I say that the radius of convergence is 0, okay? And the interval of convergence is, how do they want me to represent this? What number is this? 10? Yeah, the interval of convergence is just the single number 0. So if you're looking at it on a number line, we're saying that our x values, the only x value we could possibly have is this right here. It's not an interval, like we're not saying it's between here and here. We're saying it's only if x is 1. I mean, sorry, if x is 0. That's the only way this thing will converge. And so the radius of this, the radius of a point is 0, and the interval itself is just the point itself. So that's it. That's the first time we ran into that. Now, we probably could have done that a lot easier. I said we could have used the root test. So I just want to show you how quick and easy it would have been with the root test, just to show you it. So if I were to do this, it was n to the n, x to the n. Now, the root test, what we do is we take the limit as n goes to infinity of the nth root of the absolute value of what's there, n to the n, x to the n. And what we want with this is we want this to be less than 1 also. So let me just double check that. This is on page 462. So if this comes out to be less than 1, it's going to converge. If it's greater than 1, it diverges. And if it is 1, then we don't know. So let's do this. That looks like a natural log, but that's not. It's absolute value. Actually, I don't need the absolute value because that's positive stuff in there. And then n to the n, x to the n can be written as n times x to the n, and then the roots cancel. And you just get the limit as n goes to infinity of, well, yeah, absolute value. Sorry, absolute value of n times x. And we want that to be less than 1, but it's not going to happen. If n goes to infinity, this thing blows up. The only way this thing will stay less than 1 is, again, if we let x be 0. So that's much cleaner. You didn't have to do any of that L'Hopital and all that, but you had to recognize that the root test would have worked here. Let's look at 11. Oh, you know what? My video is probably getting close. I can probably do one more, and then I have to do a different video. All right, n equals 2 to infinity. Negative 1 to the n, x to the n over 4 to the n natural log n. Yeah. All right, I'm going to do a ratio test here after I check this text message. Okay, so ratio test, limit, n goes to infinity of, okay. I'm going to plug n plus 1 into this, so negative 1 to the n plus 1 times x to the n times x over n plus 1 in there is 4 to the n times 4, and the natural log of n plus 1. Can't do anything with that. Then times, flipped, 4 to the n natural log n over negative 1 to the n x to the n. Need that less than 1. Got some good cancellation here, 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 here. And don't need to worry about the negatives. So we are at the limit as n goes to infinity. All right, let me get all my n stuff together. On top, natural log n. On the bottom, I have a 4, natural log n plus 1. Times, over here, I just have an x. Need that to be less than 1. And now I will try my hand at this limit. I get infinity over infinity. Let's try L'Hopital once. This will become derivative of the top, 1 over n. Derivative of the bottom, 4 stays, but then this drops n plus 1 on the bottom. Forgot my x, times x, less than 1. Flip this over, limit, n goes to infinity. When we flip, the n plus 1 goes to the top, and the 4 goes to the bottom, times x less than 1. Now as n goes to infinity, I do L'Hopital on this, and I get 1/4. So I get absolute value 1/4 times x must be less than 1. And using what we did earlier, bringing the 1/4 outside, multiplying both sides by 4, absolute value of x has to be less than 4. Therefore, my radius of convergence is 4. And I need to check my endpoints, right? So far I know this. Let's check the endpoints. So let x be 4 to start. Sum n equals 2. It was 2 to infinity. And -1 to the n, x to the n, so 4 to the n over 4 to the n natural log n, 4 to the n natural log n. And these don't matter, right? They're gone, so this is going to be sum n equals 2 to infinity of -1 to the n times 1 over natural log n. This is an alternating series, and so I'll run the alternating series test on this. Let's see, with time constraints. I guess we could do alternating series test. Might be hard to show. Well, let's do it. The second thing I need to show is the limit as n goes to infinity of 1 over natural log n goes to 0, which it does. It's 1 over infinity. And then I have to show it's decreasing. So I have to show b sub n is greater than b sub n plus 1. So 1 over natural log n is greater than 1 over natural log n plus 1. And then that's natural log n plus 1 is greater than natural log n. If I take e on both sides, I get n plus 1 is greater than n. Cancel the n's, that's true. So that would be what? Convergent, right? Alternating series. Yep, so that's convergent if x is 4. Now if x is -4, some things are going to change. So let's try that. So if x is 4, that means I do want to include that. If x is -4, let's see how we change. It becomes up here -4 to the n, and then down here 4 to the n. And so when I redo this sum, I'm going to peel off on this a -1 to the n times 4 to the n. And this -1 to the n and this -1 to the n come together and become a 1. So I just get 4 to the n over 4 to the n natural log n. These cancel, sum n equals 2 to infinity of 1 over natural log n. And what we'll do for this one, since it's not alternating, we'll just do a comparison. A comparison? Or you want to do a ratio comparison? I'll just do a comparison, just a direct one. I'm going to compare it to sum 1 over n, which is harmonic. This diverges. So what I want to show is that 1 over natural log n is bigger than 1 over n. And if I do my little thing here, n is bigger than natural log n. You can take e on both sides. E to the n is bigger than n. That's true. I mean, if you just graph those two, this is n, right? But just the dots. E to the n exponential function grows faster. So that's it. I wonder if I compared it with the ratio, limit comparison test, if it would have worked out cleaner. It doesn't matter. We know that it diverges, and so therefore I do not want to include that. So the interval is -4 to 4 there. Okay, that's all I can get on this video.